Here, we have been given a system of linear equations like this, two linear equations, and because they are linear, we know we can take a coordinate frame and plot them as straight lines like this. So this is equation A, that is line A, and equation B, that is line B. And the solution lies at their point of intersection. But although we can readily see that solution in the graphical form, things are not really easy when only the equations are given to us. So the situation is more like this, where we see or rather know that the two equations are two straight lines, but we can't readily see their point of intersection. It is kind of locked inside a mystery box like this. So we do see those two lines going in, but we have no clue where exactly those two lines intersect. So how to solve this problem? Well, if we can manipulate these two lines from outside the box without disturbing their point of intersection inside, then maybe we have some hope. And we have just the right trick for doing that. We have seen that in the previous video, where we had these two lines, line A and line B, or equation A and equation B, if you will, and we combined those two in what is called as their linear combination. So we took the second line or the equation of the second line, multiplied it by some constant, say f here, and simply added it to the first one. So when we do this, we again get a linear equation, and therefore it can be plotted as a straight line, a line C, let's call it. And this line C also passes through the point of intersection. So if we change this factor f with which we are multiplying, the slope of line C, the third line, simply changes, but without changing the point of intersection. So we can take any value of f, making this C horizontal or vertical, or we can make it even coincide with one of the lines. We can do all sorts of things. So that is where our hope lies. We can do linear combination of the two equations. And that is precisely what matrices do. So let's write this equation in the matrix form. We have written these coefficients 3, -1, 1, and 1 of x and y over here in the coefficient matrix. And this right hand side 7 and 5 we have written as a column on the right side. In fact, we can have an even more concise form of this by simply adding this column to this matrix over here. This is called as an augmented matrix. And then we start doing what are called as the row operations. Row operations basically aim at eliminating one of these variables. And we keep eliminating the variables until we get some simple equations. So here we see there is 3 here. So had there been a 3 here, we could have simply subtracted and eliminated. Let's multiply the second row by 3. So we'll do that to get a 3 here. And now with both these elements as 3, we simply subtract row 1 from row 2 to get a 0 here. And now we have equation 4y is equal to 8. Simply dividing by 4 and we get y is equal to 2. So we have got half our solution. But what we have really done in terms of the graphics here, well, we have taken this line B or the second row and we have simply rotated it from outside by taking linear combinations until it becomes horizontal. And a horizontal line, we know, have an equation of this kind. Y is equal to constant. In this case, y is equal to 2. All points on this line have y coordinates 2, whether they lie outside the box or inside this box. So let's continue further in this direction. Now we see there is a -1 here and a 1 here. So if we add the 2, this will become 0 and y will get eliminated. So let's do that. We'll add R2 to R1 and we got a 0. This equation now reads like 3x is equal to 9. But we simplify it further anyway by dividing by 3. So R3 upon 3 gives us x is equal to 3. And that is our complete solution. So what it means graphically? Well, this time we have taken line A and we have rotated it until it became perfectly vertical. And now we can read off its equation as x is equal to 3. So all points on this line have x coordinate 3. The point inside, the point of intersection, is not an exception. It will also have a x coordinate 3. So our solution is complete. So let's reveal that mystery by opening the box. So that's our solution, 3, comma 2. So the entire process can be summarized something like this, that initially we keep our equation 1 or line A intact. It anchors itself and offers support to the second line so it can rotate and become horizontal, thereby eliminating one of the variables. Then the second line in its turn plants its feet and offers support to the first line, line A, so that it can rotate and become vertical like this, and thereby eliminating even the second variable. And that is how both these lines work together in tandem towards the solution. And that is the essence of row operations.